So today we're going to begin our first lesson on this unit of electricity, and we're going to look at static charge. Let's look at our objectives for today. The first is to demonstrate that charged objects exert forces, both attractive and repulsive. The second is recognize that charging an object requires the movement of charge, not the creation of charge. The third, we'll be able to describe the differences between conductors and insulators. And then the fourth, describe the mathematical relationships between electric force, charges, and distance. This is known as Coulomb's law. All right, so let's start with the basics of charge interaction. You probably remember this back from maybe middle school science. What do we know about opposite charges? A positive and a negative charge, they attract each other. Like charges, whether they're both positive or both negative, repel. Now, how about a positive charge and a neutral charge? Neutral meaning an object that is neither positive nor negatively charged. Well, a positive object will be attracted to a neutral object. And the same holds true for a negative object. A negatively charged object will be attracted to a neutral object. So neutral objects will attract either a positive or a negative charge. Now, where does this charge come from? What is the source of charge? So we can start with a microscopic view with the atom. Here's an example of a helium atom that's made up of neutrons, protons in the nucleus. The red are protons with a positive charge. And then we have two electrons that orbit around the nucleus. That's kind of a classic model for an atom. And the electrons are negatively charged. Neutrons, by their name, are neutral. They have no charge. Now, all matter is formed by atoms, and different combinations of atoms results in different electrical properties. Now, what do we mean by that? It has to do with the fact that electrons are negatively charged but are weakly bound to the atom. In other words, an atom can easily give up electrons or add electrons. Protons are positively charged and very difficult to remove from the atom. They are in the center at the nucleus, and unless we basically split the atom, it's very difficult to add or remove protons. Therefore, when we talk about an electrostatic behavior, meaning the charge on an atom or objects, it's always explained by either adding or removing electrons. It's the movement of electrons that changes the charge of an object, never the protons. So let's look at charged and uncharged objects, right? An uncharged or neutral object would have equal numbers of protons and neutrons, right? In this case, there are 4 protons and 4 electrons. Now, if we remove electrons, would the object now become positively or negatively charged? Well, we've reduced the amount of negative charge. We have more positive than negative, so we are going to have a positively charged object. So we make an object positive by removing electrons. Now, how about if we add electrons to it? It's now going to become negatively charged. So we charge an object negatively by adding electrons to it. Okay, so the object's charge depends on the net number of electrons versus the number of protons. So what's the difference? Okay, if the number of electrons is less, it's going to be positively charged. If the number of electrons is greater than the number of protons, it will be positively charged. Now, we've talked about charge. In physics, we have a standard unit of charge called a coulomb. The symbol for that unit is capital C. And 1 coulomb is made up of a particular number of electrons or protons. Okay, remember, they could be either positive or negative. And it's a lot, right? 1 coulomb is equal to 6.24 times 10 to the 18th electrons, or it could be protons that would represent a positive unit of coulomb. The charge on a single electron would be 1 over that, right? So 1.6 times 10 to the negative 19th coulombs is the amount of charge on a single electron. And we refer to that as an elementary charge. It's the smallest unit of charge, right? Because since charge is based on an excess or reduction in electrons, this is the smallest amount that we can change the charge of an object, by adding a single electron. Now, just to give you a feel for how much a coulomb of charge is, a typical lightning bolt can carry 5 to 25 coulombs of charge, right? That's an enormous amount of electrons that flow from the charge up in the clouds down to the ground. And a lot of energy in that. Scientists have been working, but not too successfully, at trying to capture the energy in a lightning bolt. Basically, how would you capture and store all this charge as it travels from the sky down to the earth? So far, not too successful at that. All right, now it's important to talk about 2 types of materials in terms of their electrical properties. They generally fall into the categories of either conductors or insulators. So a conductor is a material that permits electrons to flow freely from atom to atom. And some of our best conductors are the metals like silver, copper, gold, and aluminum. So these are materials that can easily give up or take on electrons. An insulator is a material that impedes the free flow of electrons from atom to atom. Okay, it makes it very difficult for the electrons to be freed up. So these are materials like plastic or quartz. Air is actually a pretty good insulator. Rubber, glass, or ceramics, often on a power pole, right? You see those little discs up there. Those are glass or ceramic discs that help to insulate the charge on the cable from the power pole itself. And if you look at the example of electrical wire up above, if you've ever taken like an extension cord or electrical house wiring, you know that the copper conductor is encased or covered with an insulator, typically plastic or rubber, and that keeps the charge from traveling from one wire to another. So let's look a little bit more. If it's a conductor, how will the charges be distributed on that surface? So let's say we have this metal sphere mounted on a stand, an insulating stand, so like plastic or paper, so that if we put excess charges onto the sphere, they'll stay on the sphere. They're not going to travel down the stand, okay? And we're gonna add some charge by touching it with a plastic golf tube, just a piece of plastic that has been charged up with excess electrons. So when we first touch it, those electrons will jump over to the metal sphere, okay, at the point of contact. But since the metal is a conductor and charges can move easily, those charges, those extra electron charges, negative charges, will spread or distribute themselves evenly across the surface. Now, why would they distribute themselves evenly? Remember, like charges repel. So those electrons are all going to move and try and get as far away from each other as they can. And the end result of that is they're going to be distributed evenly across that conducting surface. So here's a little bit different way of presenting this concept of insulators and conductors. We talked about the different types there. There is a special case we call semiconductors, and these have some unique electrical properties. You see silicon and germanium. Silicon is used as the basis for basically all electric semiconductors, so computer chips and memory chips, processors are all typically built on silicon. Some are using germanium. It does a little bit better at faster speeds. All right, so let's see if we understand this concept. One of these isolated charged spheres is copper and the other is rubber. Okay, the diagram depicts the distribution of excess negative charge over the two surfaces. Can we tell by looking at their distribution which one is copper and which one is rubber? Well, remember, if it's copper, it's a conductor and the charges are going to distribute themselves over the surface. If it's rubber, the charges will basically stay in place wherever you first applied them. Okay, so sphere B would be a uniform charge of distribution, and that would be our copper. And the sphere A would be a non-uniform distribution of charge, that would be our rubber. All right, so we've understood what the nature or source of charge is. It's produced by adding or removing electrons. We know what the actual measure is for the amount of charge, the coulomb, and we know about their interactions, right? Opposites attract, like charges repel, and either charge will be attracted to a negative. Now, when we say attractive, it's actually an attractive force or a repelling force. So let's talk about what actually determines that force. How can we calculate it? How is it related to the charge? Well, let's relate this to what we've already studied about gravitational force, right? If we've got somebody standing on the surface of the Earth, we have gravitational force pulling down. It's the attraction, right, between the human and the planet. Now consider an attracting force acting on you that is billions upon billions of times stronger than gravity. Now that's real. So if it's real, why doesn't it just crush us, right? If it's billions of times stronger than gravity. Well, it turns out there's also a repelling force that is also billions and billions of times stronger than gravity. So those two forces, the attractive forces and the repelling forces, tend to balance things out so we actually don't feel that electric force, right? But in our body are billions and billions of atoms and molecules, and they have electric properties. They're constantly attracting or repelling each other. So we kind of have that tug of war going on in our body the whole time, but we generally don't feel it because they tend to cancel each other out. But these are real. These are real forces, and we call them electric forces. So that takes us to something called Coulomb's law. So Coulomb's law gives us the relationship between the force, the amount of charge of each object has, and the distance that those two charges or objects with charge are separated from each other. It also includes a constant K called Coulomb's constant, 9.9 times 10 to the 9th. It has some strange units there. That's just so that our final units turn out to be in units of force, right, or newtons. So if we put the amount of charge in coulombs, the distance in meters, and our constant in here, we will get the electric attractive or repulsive force in units of newtons. So Coulomb's law gives the magnitude of the force, okay? And this is what we call a mutual force. Q1 is going to attract Q2, and Q2 is going to attract Q1, right? They're equal in magnitude, but opposite in direction. So really very similar to gravitational force between two objects. The question is, what direction will the forces be? Right? The equation gives us the magnitude of the forces, but not necessarily the direction. So to find the direction, we have to look at the actual nature of the charge. Are they positive or negative? So let's look at case one here, force one, or force exerted by Q1 on Q2. So notice these are opposite charges, and we know that opposites attract, right? So Q2 is going to be attracted to Q1. So if we say the force exerted by Q1 on Q2 would be from right to left, right? It'd be to the left towards Q1 because they are opposite charges. What if we had them similar charges, right? What is now the force exerted by Q1 on Q2? Well, we know like charges are going to repel each other. So the force on Q2 from Q1 would be to the right. See if you can figure out what direction the force would be now on Q1. Well, they're like charges, so they're going to repel. So Q1 is going to be repelled by Q2. So that would be to the left. And one more. Force exerted by Q2 on Q1. In this case, they are opposite. They're going to attract. So Q1 is going to have a force applied towards Q2. Okay, so Coulomb's law gives us the magnitude of the force, but the direction we have to look at the types of charges of the two objects involved. All right, let's try a couple more. So in this case, opposites attract. Q1 would be attracted to Q2. Force of Q2 on Q1 would be repelling away from Q2 to the left. Force exerted by Q1 on Q2, they're like charges, they're going to repel. So Q2 would be to the right. And the last one, force exerted by Q1 on Q2, they're like charges, they're going to attract each other. So Q2 will be pulled to the left. All right. So let's just do a little comparison here, right? We had Newton's law of gravitational force that was directly proportional to the product of the masses and inversely to the distance squared, and it included this constant, universal gravitational constant of g. Coulomb's law looks very similar, right? Instead of mass, we have charge. They're still inversely proportional to the distance squared, right? The force adheres to the inverse square law, and it includes this constant of k. Now, what's different is that the gravitational force is only an attractive force, right? Two objects with mass will always attract each other. Electrical force could be attractive or repulsive depending on the nature of the charges for Q1 and Q2. But again, both are inverse square laws. They vary inversely with the square of the separation or distance between the two objects. The magnitude for our universal gravitational constant is very small. The magnitude for the electric force or Coulomb's constant is very large, 9 times 10 to the 9th, right? Remember, electric field forces are generally much stronger than gravitational forces. Gravitational forces, in terms of all the forces in the universe, are generally the weakest. All right, let's go through one example and see if we can compare electric and gravitational force between two objects. They have a distance of 1 meter, they both have a mass of 1 kilogram, and they both have a charge of 1 coulomb. So the electric force, if we plugged all that in, right, if we have 1 for Q1, Q2, and distance, it's just going to be our K value, which would be 9 billion newtons. That's a huge amount of force. You would not want to be standing between those charges if they were opposite and attractive. The gravitational force would be very, very, very small. Okay, so an example of how much stronger electric force is than gravitational force. All right, let's do a calculation with kind of more realistic charge levels and dimensions here. We have two spheres. The first has a charge of 6 microcoulombs. Now, a microcoulomb is 10 to the negative 6th coulomb, so it's 1/1,000,000th of a coulomb. So we could write that in scientific notation as 6 times 10 to the negative 6. And it's 4 centimeters away from charge B that has a charge of negative 6 microcoulombs. Okay, so we have opposite charges. We want to find the force, both the magnitude and the direction of sphere B on sphere A. So what do we know? We know the charges of each and the distance, right? We're going to plug those into Coulomb's law, and we get 1.0 times 10 to the second newtons, or about 100 newtons worth of electric force that sphere B is applying on sphere A. Now, what will the direction be of the force on sphere A? Well, we know it's going to be attracted to B, so the force is going to be to the right, towards object B. All right, so there's an example of using Coulomb's law. So that's it. We know that charges can either exert attractive or repulsive forces. We know that charge is created by the movement of charge, not just creating charge out of nowhere. And we can describe the differences between conductors and insulators, and the relationship